Hey guys, Stat 1150, central limit theorem means. We're going to focus on this video on the easiest part of the central limit theorem, which is dealing on distribution of sample means. So that's kind of going to be an important topic. So distribution of sample means. And we'll call that X bar, because that's what it is, sample means. Students struggle with this material, and I think I'm very compassionate about students who struggle, but I don't understand it, because really there's going to be a lot of notation, a lot of different ways of looking at things, but if you just pay attention to really just one fine detail, these things are much like the normal distributions that we've been studying before, with a couple of little changes. So first of all, what's the motivation? Why even care about central limit theorem other than we've told you got to complete statistics for you to get your degree? But in studying statistics, why do we even care about the central limit theorem? Well, guys, at the end of the day, it comes down to the relationship between samples and populations. Now, the ultimate goal in this class, the ultimate goal in learning statistics, is to be able to take information from a sample and generalize to the population from which it was drawn. And we call this inference or inferential statistics. So, for example, if I had a new teaching technique that I thought would benefit students at Shawnee State University, then my population under study is Shawnee State University students. Or maybe even I have a teaching technique that I think would be effective for all students in the state of Ohio. Then my population would be all students in the state of Ohio. Well, if I wanted to try this out, I couldn't necessarily implement this new teaching technique on every single person in the population. I would probably have to go take a sample and use this information to make an inference about the larger population. You see this happen all the time in presidential elections. One of our recent elections where we had Trump versus Clinton. People wanted to know, how people, especially in the swing states, Pennsylvania, Ohio, Florida, Nevada, how those people were going to vote. And there's no way in the world you could go out and ask each and every person in the population, so these polling agencies would take samples and make an inference about how everyone was going to vote. And I tell you, they didn't do a very good job, but I'm not going to get into the reasons for that. In order for us to build properties and important techniques, I guess, that we're going to use in inference, we first study the reverse. And the reverse is beginning with information about a population in order to determine the likelihood of getting a sample from it. Start with the population, determine the probability of getting a particular sample characteristic drawn from this population. Now, depending on the direction we're going, if we're dealing with probability, then I must know the values from the population from which I'm drawing to determine the likelihood or probability of getting an unknown sample from the larger population. Let's keep it simple here. Let's say our population is a deck of cards. Deck of cards, I know all about that, don't I? I know there's 4 suits. I know there's 4 aces. I know there's 4 kings, hearts, diamonds, spades. I know that. But if I choose out 3 cards at random, I don't know what I'm going to get. But because I know the construction of the cards, I can determine the probability of, for example, getting 3 aces. I could do that. I could determine that based on calculations and probability. Now, let's say that I come in and give you a population and I tell you that we have 5 cards here, but I don't tell you what those 5 cards are. What's the probability of drawing an ace from those 5 cards? Well, you can't calculate that because you don't know the probability from which you are drawing. So guys, you must know the population from which you're drawing to determine the probability of getting a particular sample. Now, let's talk about the reverse. In inference, the ultimate question is about the population from which you're drawing. What percentage of people were going to vote for Trump? Well, I don't know. So I'm going to go out and get a sample, ask my sample what percentage of them are going to vote for Trump, and use that to make an inference about the larger population. So what is known and unknown completely switches. The unknown is the population value. The sample, well, we know it because we went out and collected it, that we're going to use to make an inference about the population is known. I'd like to know the mean IQ for students at Shawnee State University. I don't know that. I really don't. But IQ tests are really, really expensive and they take a long time, so I couldn't give a IQ test to every single student at Shawnee State University. Be too time consuming, it'd be too costly. I take a sample. I pull out 15 students. I give all of them an IQ test. I divide their average or their sum of IQ by 15. I get their average. I know it. I can use that to make a prediction. I can use that to make an inference about what is unknown. Now, these things over here in a sample are called a statistic. These things over here, and ignore this right here, are called a parameter. So, for example, let's say the ACT for all SSU students is 20.6 with a standard deviation of 5.9. What do I know? Because I said all, this is a parameter. It's my population. I use different language here. Again, it's a parameter versus a statistic. I use a different notation. For the mean, I would do 20.6. For the standard deviation, I would use 5.9. Most importantly, guys, I want you to understand that the notation changes whether we're with a parameter and statistic, population and sample, as compared to an example like this. The mean IQ for students in my Stat 1150 class is 102.8. The standard deviation is 14.2. Guys, the students in my Stat 1150 class constitute a sample, which represents a statistic and not a parameter. So when I start talking about the mean, I'm going to use a different notation. Instead of mu, I use x bar. And instead of sigma for the standard deviation, I use Sx, 14.2. So guys, contrasting that with what I put on the previous page. I'll do some fancy folding here. Over here, I was talking about the ACT for all Shawnee State University students. That was my population. This represented a parameter. I used mu and sigma instead of x bar and Sx because I'm representing this illustration up here as a sample. Now, let's go back to this original drawing of the relationship between a sample and a population. If the end goal in this class is truly inference, and trust me it is, The most important topic we study in statistics is inference, where we take information from a sample and use it to make a statement or a generalization or a prediction about a value from a population. Again, this is known because we've collected it. This is unknown because we're trying to make an inference about this unknown value. If the reverse of this is truly probability, as I just told you it is, and trust me it is, where the population value is known and we can determine the likelihood of getting a sample, which is unknown. We don't know what we're going to get because we take it at random. So this is known, this is unknown. We can determine the likelihood of getting a sample using probability. Now, let's think about what we have learned so far. We have learned so far using the things I taught you about a normal distribution, that if I have a mean IQ of 100 and a standard deviation of 15, so this describes IQs for everyone, for our population, I can determine the likelihood of choosing someone at random. I'll tell you what, I want to get this a little clearer. I can determine the likelihood of getting someone at random and them having an IQ greater than or less than any value, or between two values. So I could determine the probability that a randomly selected person has an IQ greater than 108, right? I can do that. And I can do that by going to StatCrunch, going to stat, going to calculator, going to normal, and I want a mean of 100. I want a standard deviation of 15. And I want to know the probability that a person has an IQ greater than or equal to 108. So I compute that, and the probability is 0.2969. So I just put the answer there, 0.2969. I can do that. I can determine the probability, and again, over here, sample size 1. I'm selecting one person from this sample, and I'm determining the probability that their IQ, actually this should be greater than or equal, is greater than or equal to 108. It's 0.2969. Now, if this cycle truly exists, if this relationship between probability and inference, if this is truly some cycle going on in statistics, as Darbo's claiming, trust me, it's true, then what I can do from the laws of probability is I can use this information to make an inference. You guys, trust me, it's all going to make sense if you just stick with me. So what we now do is we can determine the probability of one person having an IQ above 108. So I am now prepared to conduct inference based on one person. Take a sample of 1. Let's say I want to know the mean, Ohio score for a particular high school. And I can get this information from the state. So I go take one sample. I take one student from that high school. I give them the test, and I make an inference about their test for every single student in the high school. Guys, that would be dumb statistics. That would be goofy statistics. I don't want to take just one person and use that information to generalize to a larger population. I want to take a substantial sample, clearly greater than 1. I want to look at the mean of my sample and use that to make an inference about the larger population. So what we know right now is we know how to determine the probability of taking one at a time. But guys, what we're going to explore in the central limit theorem is how do we determine the probability when we take more than one at a time. Well, guys, it's called the central limit theorem. Now, problem. Problem number 1. We know IQs are normally distributed with a mean of 100, standard deviation 15. A person is selected at random. What is the probability? Their IQ is less than 118. A person, think, n equal 1. Well, ladies and gentlemen, you do not need the central limit theorem. You need to go to Google Chrome and you need to put in 115 and you need to change this to less than, and you need to put the value in of 118, and you need to hit compute and get your answer 0.8849. That's all you need to do, just like we've done before. You got your answer. Problem 2. IQs form a normal distribution with a mean of 100, standard deviation 15. Twelve people are selected at random. What is the probability their mean IQ is less than 105? Guys, you can't work this problem with what I taught you up here, taking people out one at a time, getting a sample one at a time. When we get into 12 people at a time, we take these 12 people and we collectively demonstrate their measures by taking the mean. Person number 1 has a mean of 108. Person number 2 has a mean of 106. Person number 3 has a mean of 128. We add those 12 IQs up and divide by 12 and get the average IQ. And because it is a sample, we use the notation X bar. We use the symbol X bar. Where this mean up here would be 100 mu because it describes the entire population of IQs. But when I take a sample, I use X bar, and overall these types of problems are completely different. Okay, now we're going to come back to this problem number 2, but we're going to develop some tools first, okay? So here's the way the central limit theorem works. First of all, you begin with a population. You must begin with a population. That's the way probability works. And you begin with this population where the mean and the standard deviation are known. Now, why is that important? Well, guys, let's go back to the original drawing that I started with. It's important because to determine the probability of getting a sample, you must know the population from which you're drawing. So you must know the distribution shape, you must know mu, you must know sigma. Okay? Now, what happens here depends on what kind of distribution you have. And for this class, we're going to keep it kind of simple. We're going to say we either have a normal distribution or we have a skewed distribution. Now, guys, remember, we talked about it earlier, and a lot of you got some easy free points because you submitted the quiz. If we have a distribution that pertains to money, then we most likely have a positively skewed distribution. IQs, ACTs, GREs, LSATs, gestation periods, all kinds of different distributions are normally distributed, but some aren't, some are skewed. So depending on what kind of distribution we have what's called the sample size restriction. Turns out if you have a normal distribution, you don't even have a sample size restriction because you need 2 to get a sample mean anyway. So 2 or higher, you can work those problems. However, in a skewed distribution, there's something magical about this 25 sample size. Okay? For all of this central limit theorem stuff that I'm going to teach you to work, if you start out with a skewed distribution or even an unknown distribution, then you do sample size of 25 for all this stuff down here that I'm getting ready to teach you to work. If you know you have a normal distribution, you kind of luck out. You just need a sample size of 2 or bigger, which you need it anyway because our focus is on a sample mean, and you need at least 2 people to add together and divide by 2 to get a mean. So if this is met, if your sample size is 2 or bigger for a normal distribution, or if you're working a problem that's a skewed distribution, your sample size is 25 or bigger, then this is met, then we can go on. Now, first thing I want you to imagine is imagine collecting all samples of size n from this population. All right, so let's just say that we're drawing from a distribution that has a mean of 12 and a standard deviation of 3, just for an illustration. Doesn't have to be 12, doesn't have to be 3, it could be anything. But just for me talking through this illustration, let's say that that's the distribution that we're drawing from. And let's say that size n, just for this illustration, is equal to 12. I don't want to do that because that would be confusing with that 12. Let's say it's equal to 10. If we're in a skewed distribution, then this stuff doesn't work that I'm getting ready to teach you. But if we have a normal distribution, it does. So guys, what I would do is I would dive into this population, pull out the first 10 people. I would get all their 10 scores. I would add their scores up. I would divide by 10. And I would get the first sample mean of size 10. I'd throw these 10 people back in the population. I'd randomly select 10 more, add up their scores. I would get my second sample of 10. Do it again. Do it again. Imagine doing it forever. It's going to be a long homework assignment, isn't it? You don't have to do it forever. What you just have to imagine is that you could do this forever, and you could create infinite number of sample means here. All of these numbers here take on a new distribution of their own. It's no longer the original population distribution that we started with. This is called the distribution of sample means, x bar. Now, central limit theorem tells us some important things about the distribution of sample means. Important characteristics of the distribution of sample means. All these numbers over here. So let's say that the first 10 people ended up having a mean of 10.8. Next 10 people had a mean of 13.2. The next 10 people had a 11.4. We wouldn't expect these things to be the same values, would we? We wouldn't expect these sample means to be the same. If we come in and pull out 10 people, we're going to get something different than we did the 10 before and the 10 after. So these things are going to vary. So that's one thing that we expect is we expect the samples to vary. And we expect it so much that we give this fancy smancy name called sampling variability. Those numbers are going to change from sample to sample. Second thing we know about characteristics, our X bars will be normally distributed. That's kind of cool. If you start out with a skewed distribution, as long as your sample size is 25 or bigger, .30 is bigger than 25, isn't it? This distribution of sample means that we could collect, in theory, will form a perfect normal distribution. Just like wham bam, thank you ma'am, magical. This skewed distribution magically turns into one of those when we stop looking at the scores one at a time and start looking at the scores 30 at a time in this situation. I'm going to do an illustration on Stack Crunch that might help. Well, we know that every normal distribution has a center value. And in the center of this, we're going to put what's called mu sub x bar. And that's kind of complicated because that's a population value with the subscript of a sample value. But I want you to know that this is the population mean of this new distribution that's composed of and comprised of, consists of, and created by these x bars. Well, guys, it turns out this thing's very, very easy to find because it's just the sample mean that we started with way back here. It's mu. It's what we had to know to even start the problem. And the final thing we know is that this sampling variability that I talked about back here can be described by what's called the standard error. It is calculated by taking the standard deviation divided by the square root of n. So the value we started with back here divided by the sample size that we were consistent with, we can find this value called the standard error. So the standard deviation of the sample distribution of sample means is called the standard error. The standard deviation of the sampling distributions. These numbers back here are going to vary. So they're going to have a standard deviation that describes that variability. They're going to have a standard deviation that describes that sampling variation, this sampling variability. And we call that the standard error. All right, gang. Let's go back to problem number 2 that we created a while ago. Problem number 2 said this. IQs are normally distributed with a mean of 100, a standard deviation of 15. That's the population I'm starting with. I draw out 12 people at random. What is the probability their mean IQ is less than 105? First thing I know, I can expect the samples to vary. If I dive into people who have IQs and pull out 12 at a time, I can expect sample 1 to be different than sample 2, sample 3 to be different than sample 1 and 2, sample 3. I can expect difference in all the samples. Second thing I can expect, I have a normal distribution. You might say, wait a minute, that I thought there was something going on about that 25. Well, there is if I have a skewed distribution, but if I have a normal distribution, I just need greater than or equal to 2. Well, guys, 12 is greater than or equal to 2. This center of this distribution will be the mean of the original distribution I'm drawing from. And the standard deviation of this distribution can be found by taking the square root over, the population standard deviation divided by the square root of n. This value is 15. My sample size is 12. I can put this in my calculator. And I get 4.33 as my standard error. Now, this distribution will be centered the same place that the other one was. One standard deviation above and below the mean will be 15. And my distribution of scores will look something like this. When my sample size is 1. However, when I have a 12 at a time, my mean's going to be the same. But my standard deviation is going to be 4.3, so I need to come over here about 4. Come over here about 4. My distribution is going to be taller and skinnier. It's an important characteristic of the distribution of sample means when I take them 12 at a time. So the distribution itself is going to be taller. It's going to be narrower. There's going to be more sample means closer to the 100 than there are scores taken one at a time. And what this ultimately helps us do in inference, when this value is unknown, it allows us to tap into more sample means closer to the value that we're trying to estimate. All right, so let's go back to the original problem. I got a whole lot of stuff going on here. How are we going to work this problem? 12 people are selected at random. What's the probability their mean IQ is less than 105? Guys, I'm just going to go to, and I'm going to put in 100, but I have to come in here and do the square root of 12. I have to change the standard deviation. I want less than 105. Hit compute, and I get my answer. My answer to this problem is 0.8759. Now, I rounded to 4 places there. make sure you round to however many places that your MyStatLab question requires you or asks you to round to. So let's just so there's no confusion and to try to demonstrate exactly how easy these problems are. We saw earlier the gestation periods form a normal distribution with a mean of 266 days. Standard deviation is 16 days. So I know here that my mean is 266 and my standard deviation is 16. 35 women, pregnant women, are selected at random. What is the probability their mean gestation period is greater than 272 days? Now let's go back. First of all, is our sample size restriction okay? Well, we got 35. But we started out with the normal distribution, didn't we? So really all we needed was 2. 35 is bigger than 2, so that's good. Then we're just going to let the stuff happen. The mean of this distribution, taken 35 at a time, is going to be the mean of the original population. The standard deviation of the distribution of means is going to be the original standard deviation divided by the square root of n, which is 35. So I'm going to just pop that in the calculator real quick so you can get a number. And I get 2.7704. Now, how are we going to work the problem? We're going to use StatCrunch. So what do I need? Mean of 266. Standard deviation is 16. You know what? A lot of students will screw it up and they'll just put in 16 because they fail to understand the central limit theorem. They fail to notice that the sample size is bigger than 1, so we have to use the central limit theorem. And the key to using the central limit theorem is to divide by the square root of the sample size. So we want greater than 272, and the probability is 0.0133. So it's not going to happen very often. However, if that problem originally said one woman is selected at random, what's the probability that her gestation period is greater than 272? Then I would need to come back and just change that to the original standard deviation, do compute, and we'll get a higher probability. It's much more likely that you can get one person with an IQ, or I'm sorry, a gestation period at that level, than it is to get 35 collectively who have an average gestation period that far from the mean. 272 is not that far from the mean, but when you collect 35 different women to get their mean gestation period, it's much more likely that only one would be that far away. Alright gang, that's all I got in this video. I'm going to give you an illustration using StatCrunch in the next video and kind of show you how this kind of works out with real numbers. So take care.